talk by Anna Melnykova, who will now come back to the main theme of this mini symposium, Hawks processes, showing us that we can do many interesting things with Hawks processes. Anna finished with like Morgan her PhD last autumn. She worked under the supervision of Eva Lecharbar and Adeline Leclerc-Sanson between Cergy and Grenoble, and she will take an assistant professor position next September at the University of Avignon. Anna, if you want to start.
Yes, the second for the introduction. Already you can hear me?
If you can go back to your computer microphone as you did before, I think it will be much better.
I'm with my computer microphone, but so I think I should have put the camera on.
That's very choppy right now.
So okay, so let me disconnect completely. I'm sorry.
Okay, so we are waiting for Anna to come back. While we are waiting, if anyone has questions for Morgan, you can take the opportunity to ask. Yes, Günther has a
Yes, in the beginning, I didn't understand one point because maybe it was too fast. You had introduced these two processes with maybe one was called X and the other X star. And I didn't see the relation between the two processes.
Yeah, I'm really sorry. So now So could you please let me share the screen?
Yes, Anna. Okay. Let me. I'm not an expert.
Anna, you are co-host now.
Yeah.
Yes, must be fine. Okay, so you see my screen?
Yeah.
You hear me?
Yes.
Okay, good. So I will not put my camera, sorry, because I want to avoid some troubles. So I will present you work which I have done with Julien Chevalier, who is an associate professor in the University of the Noble Alps, and with Renzo Becanis, who is now a postdoc in GQLinks. So I will talk about the diffusion approximation of multi-class Hawks processes. So first, I will start with photos of my co-authors so that we have a bit more kind of personal presentation, and also everything I'm going to talk about. It's a subject of the publication in Advances in Applied Probability. So like, if you see the slides later, you can check the paper. So I think at this point, maybe it doesn't make sense to make a very solid presentation introduction to Hawks processes, but I will still recall very shortly that it's a very convenient network, I mean, a very convenient framework if you want to model an activity of a big network of neurons, because we can only keep track of spiking events in the binary form, like we just count the events. We can use the memory. So on the contrary to Poisson process, we have something which can keep track of all the previous events which happen. And also what is good is that we can model the interactions between different populations of neurons. So that's why we are talking about multi-class processes. Hawks process is described by its conditional intensity. So usually there is some part which is, let's say, corresponds to the baseline intensity, and also some part which comes which models the memory, or can also model interactions between different populations. So here we will consider a framework which is proposed, I think, by François Delarue and Stefan Minotti, and also by Suzanne Dietloff and Eva Löcherbach in their paper from 2017. So we consider K population of neurons. So here I will talk for simplicity about two populations, but like all the results, they can be generalized also to no matter which number K. Then we consider some intensity lambda kn. So each spike in each population has its own intensity. But all that we generalize a bit because we consider mean field framework. So what does it mean? It means that we don't care about interactions between, let's say, one specific neuron, how it influences another specific neuron. We are only interested in interactions which happen between different populations. Okay, so that's why we just consider some very big network with a constant number, constant proportion of neurons in each population, which interact somehow, like depending on our functions H, KL, which are synaptic wave functions. Now a bit more about these functions. So we will choose a very specific form of this synaptic weight function, so also called a memory kernel. So we will take this shape. So it's called the Erlang kernel. So they're kind of exponential, but not completely. So here we have one constant which models, let's say, just a sign of the population, so whether it's inhibitory or excitatory, so it can be just -1 and +1. Eta k models kind of the depth of the memory order. So together with parameter nu k, they say to us which moment in time is the most important for us, like if you want to, let's say, predict or see the current intensity. Yeah, if this ratio is big, it means that all the events are more important. If kind of both parameters tend to infinity, but the ratio is constant, then kind of only one specific moment in time is important. So what are we going to do with this process? So first, we want to study its dynamics, and in fact, it will be more simple to do that if we pass, let's say, from kind of from this integral differential form to something simpler. So if we take these functions and then we integrate this part several times, we can describe the process completely as a piecewise deterministic Markov process, which resembles, let's say, just an ordinary differential equation, but with some jump term. Okay, so already, like, what is our process xkj? That's a kind of integrated intensity process. So if we have activation function fk and this process x bar, then we can describe completely the the family of jump processes that kn. So that's one simplification. Another simplification, let's say, if we talk about really big network of neurons, then in fact we can pass to something more pleasant to work with, let's say. So in order to pass from this, let's say, ODE with jump term, which can be a bit difficult to analyze, we can replace this jump term, which is basically like average behavior of the process in the past, by diffusion term. So we can approximate this part by a diffusion process. So like some part which will be, let's say, deterministic, so it will be a drift term, and some part which is which models, let's say, stochasticity, which we have in our system by some Brownian motion. So in other words, we can pass from this precise deterministic Markov process, which you have seen on the previous slide, to stochastic differential equation. And this stochastic differential equation, which will describe like quite precisely the dynamics of the whole process. How exactly it looks like? So here I will introduce just some notations. So we will have some part in the drift which will be just linear. So we have some kind of cascade term, and there will be one part which comes from this approximation, let's say, of like jump process by diffusion given by Bx. So here, what is interesting is that all coordinates of the process xt, they will contain just zeros in this vector Bx, except for the very, very last one, which models, let's say, the interaction between the populations. And the same holds also for the diffusion term. So we have, let's say, zeros everywhere. So we don't have any Brownian motion influencing directly the coordinates, except for the very, very last term, which is non-zero. So here, what is interesting is that we have kind of degenerate diffusion, but so why is degenerate? Because we have only one source of noise, so to say, but it's not completely degenerate because thanks to this cascade structure, this matrix A, our Brownian motion propagates to each element of the system. So that's what we mean usually when we talk about hypoelliptic diffusions. Okay. So now again to just I can print a bit what we have done, like, and what kind of dynamics each process represent. So when we talk about ZKN, we talk about usual counting process. So here, like, each line represents one neuron, where like we can see black dots that's spiking times of each individual neurons. So here also what is interesting is that you can see that in the very beginning, like, this part is more dense, so we have much more spikes. And then we have some kind of stripes, so depending on your screen, you can see them or not. When we pass to the process X, we don't see, let's say, individual spikes anymore, but we can see how systems interact. I mean, populations interact. So, for example, here we have excitatory population, which has, let's say, positive to gradient intensity, and we see that they like this population oscillates somehow in the long term with certain kind of dependency on the second population, which is inhibitor. Okay, so we cannot say exactly which neuron has spiked at each moment, but we can at least see that those populations, they interact. So first result of our paper, basically, let's say, well, not a generalization, but like just reinforcement result of the paper by Susanne and Eva. So we prove that our piecewise deterministic Markov process and diffusion process, they converge in a strong sense. So let's say we can obtain the strong error bound on the norm between two processes. So that's good news. Bad news is that we see that strong error bound kind of has some exponential term. It means that in the long run, both processes, they kind of diverge. But of course, when we have a really like a lot of neurons, then on some short like fixed time interval, we can observe more or less the same dynamics. So how do we prove that? In fact, the proof is, let's say, quite technical. Basically, like very rough words, what are we doing? First, we are decoupling the population, so we want to consider them as two independent processes. Then we rescale time for Hawks processes. So to say, we want to have something which is which spikes at the same constant rate, like on some fixed intervals of times, not equal, of course. So like this, we can consider, let's say, a Poisson process. And then we construct Brownian motion Poisson process on the same probability space, and we use a result from the literature which says that we can bound, say, the norm between the two. So here, the exponential part in our proof comes from this result by Etienne and Kurtz. And if you want to have something better than that, then you have to go, let's say, all the way back to the question of like models of continuity between of Brownian motion. So now just an illustration of what I was talking about. So it's not real illustration, let's say, because I said that we can construct a Brownian motion Poisson process on the same probability space, but it doesn't mean that we can do that, say, physically. So we cannot just fix some seed in, for example, R and simulate both processes with the same stochastic, let's say, influence. But nevertheless, even if we cannot do that, we can see that when we increase number of neurons, so both dynamics, so both trajectories of processes, so PDMP and diffusion, so they kind of coincide, and like on the fixed time interval, we can consider both of them as as basically describing the same thing. These results can be used, for example, to prove also that our piecewise deterministic Markov process converges to some ODE, in fact, but that's not what we are doing here. So what we will be interested in, we will be interested in studying this resulting diffusion. Why it's cool? Because from a theoretical point of view, it's quite easy to study, for example, how it depends on parameters. We can talk about some bifurcation points. We can study its long time behavior, also if it's ergodic or not. And also we will show that it will be much faster to simulate. So in other words, if you want to study really how our system of interacting particle develops, it's easier to do that if we work with the diffusion. We will start with the simulation part, let's say, because that was the main goal of our paper. So we have some high dimensional system where dimension is given by a parameter. We have diffusion with nonlinear drift and the general diffusion coefficient. So we have hypoelliptic system. What we want to do, we want to propose some good approximation scheme which helps us to study its behavior on some time interval with a fixed time step. So classically, what is done, we use some, let's say, piecewise deterministic schemes like Euler-Maruyama, but they don't work very well, especially for models describing, for example, neuronal dynamics, because they are really nonlinear. And also, even if some schemes converge, they don't necessarily preserve the properties of the underlying process. So that's also something which I will illustrate. So what we will do, we will use, let's say, our almost linear structure of the scheme of the system, and we will try to use a splitting scheme to approximate the solution of the system. So splitting for SDEs was used really often, especially in recent years, and especially for neuronal models, because, as I said, it works really well for models where Euler-Maruyama fails. So first, I recall our diffusion. So we can rewrite, like if we just do some, let's say, transformation of the system, we can rewrite it in the following form. And first thing which we can observe is that it's indeed hypoelliptic. So if we do this transformation, we see that we have some non-zero part in each element of the system. So that's something which we will use later in the analysis. So then to write a splitting scheme, as I said, like we can split the whole process in part with linear drift and also without any diffusion part. So we have just ordinary differential equation with linear linear part, and we have some part which is non-linear and it's not deterministic, but it contains a lot of zeros. So we can write the solution of both parts explicitly. So again, the first solution, but just a solution of ODE. Second part, that's a solution of of an SDE where we have, let's say, some constant components. Okay. So once we have done that, we can do actually splitting. So we can use, let's say, several ways to write the resulting solution. Here we use primarily lead-rotor splitting. So we just write a convolution of both, and we approximate on each small time interval the process xt by this guy. So I mean, it's conditional approximation. So we use the previously computed value to approximate the next one. And once we have written that, we see that it's kind of a discrete analog of the, let's say, exponential transformation, which we have seen a few slides before. So first result of concerning the splitting scheme is that it's convergent with mean square order 1. So kind of everything is good. We can be sure that for delta being small enough, we will converge to our real solution. So the proof is quite classical, let's say. So we compare it to the usual Euler-Maruyama scheme. We show that both of them, they converge with the same order. So now that will be probably your first, the first question. Kind of why bother with everything? We say that we have two schemes which converge with the same rate. So I will show you that it's not enough, in fact. So here just a few remarks on the splitting. So first, kind of I just focused on one decomposition, but it's not unique. We can split our system in more components. Also, we can use not only lead-rotor, but for example, strang splitting. But here, for the sake of simplicity, we will talk only about lead-rotor splitting. So first result as an illustration of the convergence rate. So we see that indeed lead-rotor splitting and Euler-Maruyama scheme, they converge with the same rate. For the strang splitting, we have probably slightly better results, but so probably theoretically we can prove that orders of convergence is slightly different, but for the moment that's not really the thing which is the most interesting. So here's the part which I will not show, let's say, theoretically, because I don't have time, but I will just show, I will say to you that our splitting scheme preserves the moments of the process. So that's not the case for Euler-Maruyama. And also I will say that the system is ergodic. So for systems with oscillating dynamics, Euler-Maruyama, it can converge, but will not really preserve the moments. So what about ergodicity? Basically, what we mean by, well, ergodicity of the approximation scheme is that whenever, like, no matter the point from which we start to approximate the process, eventually we will converge to some, let's say, stationary state, and well, we will stay there for some point, for some moment. In general, it's a stronger result than just convergence, let's say, in the mean square sense, because well, let's say it's not asymptotic. So we have good behavior, let's say, of the system, even for a time of discretization being fixed to some specific value. Okay, so no matter our delta, we will kind of converge to some good state. So how do we prove that? So we establish a Lyapunov condition on our approximated process. Then, thanks to our convolution type structure of the scheme, we show that it's hypoelliptic. As a result, we can control, say, the behavior of our system, meaning that we can find some, let's say, Brownian motion, like, okay, it will be just normal variables in our case, which help us reach a certain state in a fixed number of steps. Okay. So now I will proceed with some pictures just to show what exactly we have. So here I will consider Euler-Maruyama scheme and our splitting scheme. So we see that when we have delta being fixed to very small value, both of them, they are identical. When we start to increase step size, then kind of we see that Euler-Maruyama behaves not very well. So already it's not preserves the amplitude of the let's say of the oscillations. So trajectories, they become really distorted when we increase delta. While for splitting, that's not the case. So we have quite good behavior even for well, very big time step. So that's the first thing. Sorry, it's a bit slow. What happens? So sorry, no. Okay. No. Well, no, it's fine. Yeah. So second thing is that even the empirical density is not preserved. So that's basically related, I think, to weak. No, sorry, not this bad. So we can see that when we have big time steps, so well, not only the amplitude not preserved, but also, let's say, the mean of the trajectory becomes shifted. So in addition to that, for some reason, we have B model density for very big time step, which is, let's say, not what we expect to see. To finish with, just very, very shortly, so why I was talking about splitting, why I was talking about SDE, so kind of why it's important, because kind of underlying idea of the whole thing that was to try to study the dynamics of the piecewise deterministic Markov process with a certain precision. So now what remains to show, that remains to convince you, let's say, that numerically for some fixed time interval, our SDE replicates very well the dynamics of the PDMP. To prove that, let's say, empirically, I can just show you that the empirical density of both processes, they kind of coincide. So now I'm talking about diffusion and the PDMP. So when we increase number of neurons, we observe kind of well, the same density with the same mean. So we can expect that well, both of them, they describe the same thing. So now, what was the interest at all, like talking about diffusion, if we can as well simulate just a point process? So the key point is that diffusion is much faster to simulate. So when we have a counting process, then depending on the intensity, which depends in its turn on the number of neurons, we can have really huge simulation time. So if you want to see some really big time interval, then like it can take really sometimes days to turn, let's say. For the diffusion, like number of neurons for us, it's just numerical parameter which doesn't influence, let's say, anything. It doesn't influence the speed of the simulation. So we can safely run a simulation for no matter which number of neurons, and we'll still have good thing, and kind of will have a reasonable computation time. Yeah, just to conclude, splitting schemes, they are good because they preserve properties of the scheme, and in general, diffusions, they are good because they help us to simulate the activity of big network of neurons at really negligible computation cost. So in a perspective, it can be integrated, for example, to some like simulation-based statistical procedures like approximation computation to compute, for example, the parameters. And I think that's it. So I hope I was in time.
Thanks a lot, Anna. Yeah, you made it